electric field due to infinite plane sheet. This is our next heading. Electric field due to infinite plane sheet. Okay. In this, we are taking a plane sheet in such a way that all of the dimensions you can say are infinite. We are taking this sheet like this. This is our sheet, and this sheet have charge density of sigma. This sheet having charge density sigma. Okay. And due to this sheet, we want to calculate the electric field produced by it. Okay. So to calculate the electric field, we know we have a single way to calculate it by the help of the Gauss law. And we know Gauss law is directly, Gauss law calculate electric field in two steps. In the first step, we will calculate the flux produced by the sheet, and then we will calculate the electric field. Okay. Now, first of all, what will be the Gaussian surface? In this case, we can take Gaussian surface as a cylindrical in shape. You can choose it like this. This is your Gaussian surface. This one is the Gaussian surface. And the area of the sheet is taken as S. If it is S, then both of the area will be S. I mean, cross-sectional area, you can say. And now, what will be the electric field? In the positive X, it is along this direction. And for the back-end side, it will be along this direction. This is your direction of the electric field. And this is also the direction of electric field. Okay. To see this sheet, you can imagine if I try to draw the cross-sectional area. Just 1 second. First, okay, we are going to complete it. Then we will see the another okay way. What will be the unit vector for this cross-sectional area? For this cross-sectional area, the unit vector always be, or you can say it is your area vector, always be perpendicular to the surface. Similarly, for this also. Okay. This is your area vector. Or you can say TS vector also. Okay. The another surface, this is your surface 1. This is your surface 2. And this is your surface number 3. Okay. Surface 1 and surface 2 and surface 3. There are total 3 surfaces. If you want to look this plane sheet from your from the front, just like you can imagine that you have a plain sheet, okay, of your notebook, okay. When you try to see this sheet from its front view, I mean from its thickness view, you can say, then this sheet looks like this. Are you clear? Are you understand it or not?
Yes, sir.
Okay. The cross-sectional view. This is your cross-sectional view and this is your front view. Okay. You can write also here. This is your front view. And this one is your cross-sectional view. And the charges are distributed on this sheet from both sides. Now, when you take a Gaussian surface, then you can draw it like this. This is your Gaussian surface. You can take it in cylindrical in shape also. Okay. This one is your surface 2. This is your surface 1. And this one is your surface number 3. Electric field lines from right hand side will be along this direction. And for the left hand side, it will be along this direction. The area vector is along this one. Area vector for the curved surface area and for surface 3 will be along this direction. Okay. I hope all of you are clearly understand the pictorial representation of this infinite plane sheet of charge. Are you clear or not?
Yes, sir.
Is there any issue to any one of you? Aisha, Akshay, Hamza, and Rufia. Any one of you have any issue in this pictorial representation? Are
No,
you
sir.
clearly understand, Hamza and Rufia?
Yes, sir.
Okay, good, good. And now, in the next step, we are going to calculate the flux. But before calculation, we should write some steps here. Consider a cylindrical Gaussian surface. Consider a cylindrical Gaussian surface having area of ends S. Then, what will be the flux through end 1? First, we are going to calculate flux through end 1. This can be represented phi 1, which is your E dot S cos theta. And you can look at here in any one of the diagram, either in front view or in cross-sectional view, the angle theta for surface 1 is 0 because the angle between electric field and the unit vector is 0. So we can write here E dot S cos theta, which is equal to E dot S.
So it should be EDS, right?
No, you can take at E dot just 1 second. You can take here as integral part also. Okay. And when you are taking integral part, because we are we are choosing a very small area here, you can take electric field at outside integration of ds. Finally, you get E into S. Okay. Both of the method is correct. This is a method of calculus. And but before this, I was trying to do it by the algebraic way. Okay. This is your phi 1 is equal to E into S. This is your equation 1. Similarly, what will be the flux through end 2? Okay. For end 2, your flux once again will be same. Phi 2 is integration of E dot S. E dot ds you can take here. E dot ds cos theta. E can be taken as outside integration of ds. Theta is again 0. Finally, you get E into S. This is your equation number 2. Similarly, flux through curved surface area. Okay, this is your phi 3, which is equal to integration of E dot ds. You can take here ds cos of 90 degree. Why? Because in this you can look at here, your electric field and the unit vector are making 90 degree with each other, and we know cos 90 is 0. Then we can write directly phi 3 is equal to 0. This is your equation number 3. Then what is the total flux? Total flux through this whole cylindrical Gaussian surface. We can write here total flux phi is equal to phi 1 plus phi 2 and phi 3. Okay. Phi 1 and phi 2 is ES. and phi 3 is 0, you can take, you can write phi is equal to 2Es. This is the total flux passing through this Gaussian surface, which we have chosen here. Are you clearly understand?
Yes, sir.
Any issue in all of you, either
No,
Hamza, any issue?
no, sir.
Okay, good. Aisha and Rufia.
No, sir.
Okay, good. Note it down, please. Remember that Gauss law is one of the best law, and okay, it is very, very easy law in which the pattern of the solution of all of the derivation is nearly same. Okay, steps are nearly same, but it is important to remember here when either either in any case, wherever you are using the Gauss law, the first thing is that you should calculate the flux, and then we can calculate the electric field. This is the reason, because Gauss law never calculate electric field directly. Gauss law always calculate the flux, and by the help of flux, we can calculate electric field. Are you clear or not? So we can say Gauss law is a two-step process for the calculation of electric field. Are you clear or not? Without flux, Gauss law is not applicable. Gauss law never calculate electric field. Are you clear or not?
Yes, sir.
Yeah, note it down, please. It is always a two-step process. The first one is flux, and the second one is electric field. All of you have noted it or not?
Yes, sir.
Okay, good. On the next page, I am going to write this equation again. Phi is equal to 2Es, right? This is your flux, which we have calculated. And now, by using Gauss law, we know the flux is equal to the total charge enclosed within the surface upon epsilon naught. Okay. Now, put here phi is equal to 2Es. 1 second, please. 1 second, please. Give this one equation number 1, and this is your equation number 2. Put put 1, I mean equation 1 in 2. We can write here 2Es is equal to Q enclosed over epsilon naught, where E is equal to, suppose that E is equal to Q over 2 epsilon naught S. You can write here, we have considered that the total charge enclosed is Q. This is your value of electric field in terms of the charge. You can write here equation number 3. But in terms of density, if you want to calculate in terms of density, then we know that this is a type of two-dimensional body. Then the charge density will always be represented by sigma, which is equal to sigma is equal to Q over S. Or we can also write Q is equal to sigma into S. This is your equation number 4. Now put 4 in 3. We get E is equal to sigma into S over 2 epsilon naught into S. S is cancelled by S. At the end, we get sigma over 2 epsilon naught. This is your final equation. Okay. Any one of you have any issue in this equation or in this calculation? Tell me, please.
No, sir.
Okay, good. Sorry.
No, sir.
Have you any issue? Aisha, I think, right?
No, sir. I said I don't.
Okay, okay, all right. Note it down, please. Note it down, please. All of you.
Done, sir.
Hamza, are you understanding? Have you noted it? Hamza.
Yes, sir.
Okay, good. Rufia and Aisha. And now in the next, once again, I'm going to take this equation. In this equation, we have E is equal to sigma over 2 epsilon naught. Any one of you can see that, all of you can see that there is, this equation is independent on R. R in the sense position. Are you clear? Independent of R. Hence, we can say that it is an example of uniform field. Okay? Uniform field. I mean, this sheet produces uniform field. Hence, we can say it doesn't depend upon the R. And if you want to draw the graph of this equation between the E and R, then you can look at here. This will be your final graph. This is your graph. Okay. It is independent of R. This is your E and this one is your R. Note it down, please. Also, this whole part, note it down. Have you noted it?
Yes, sir.
Okay. Now we are taking an example. Note it down, please. We have two infinite plane sheet of charge here. This is your first plane sheet of charge, and the another plane sheet of charge is this one. This plane sheet of charge having charge density sigma 1, and this is of negatively charged, so it is taken as sigma 2. Okay, there are total 3 regions are given. This is your region 1, or you can say this is your point 1 here, and this one is your region 2, and this is your region 3. It is saying that calculate electric field in region 1, 2, and 3. Note it down, please. This is your question. Have you noted it? Hello.
Yes, sir.
Have
Yes,
you
sir.
noted it? Now, remember that previously we have calculated the electric field due to plane sheet of charges sigma over 2 epsilon naught. Okay, this is our main equation which is required here, sigma over 2 epsilon naught. In this question, it is asking that calculate the field in all of the region 1, 2, and 3. Okay. Anyone of you can tell me, please, what will be the direction of the electric field lines or electric field in region 1 due to sigma 1 plate? Anyone of you? What will be the direction of electric field in region 1 due to sigma 1? It is,
Outwards.
yeah, it is outward. Good. Along plus x-axis or along minus x-axis? Hello. Along
Both.
plus x direction or minus x direction? Akshay,
Yes, sir. I'm thinking.
what will be the direction of the electric field in region 1 due to sigma 1?
So positive.
Aisha and Rufia. Aisha, what will be the direction? And Rufia. We have already studied that due to the positively charged body, electric field is always away direction, away from the charge. If it is negative, then the field lines always be towards the charge. Do you remember or not?
Yes, sir.
Do you remember or not?
Yes, sir.
Okay. Now, the direction is in region 1 due to plate sigma 1 is away. Okay. This is the direction of the field in region 1. Are you understand or not?
Yes, sir.
In region 2, what will be the direction along plus x or minus x? In region 2 due to sigma 1. Once again, it will be away from the charge. I mean, away from the positive plate. In region 3, once again, it is away from the positive charge plate. Are you understand?
Yes, sir.
Are you understand or not? Rufia, are you understanding or not? Hello. Hello. Rufia and Hamza. Hamza,
Yes, sir.
are you clear?
Yes, sir.
Okay. In the next, what will be the direction of the electric field due to negative charge plate in region 3? Akshay. In region 3, what will be the direction of the field?
Region 3.
It is towards the plate because it is a negatively charged.
Okay.
And in region 2, in region 2, once again, due to sigma 2, it is towards the charge. Are you clear? In region 3, it is towards the negative charge. Are you clear? All of you are understanding?
Sir, can you
Yes,
explain?
sir.
Sorry, any one of you?
Sir, can you explain again?
I think you are Hamza, right?
Yes, sir.
Hamza, remember that the electric field lines due to positive charge always go away from the charge, and due to negative charge, it always be towards the charge. Are you clear?
Yeah.
And in such like of these cases, okay, like this question, when we are drawing the electric field due to any one of the sheets, suppose that this is your first sheet, then there is no need to see the another sheet, I mean sheet number 2. Okay, you should concentrate only on the sheet 1 if you are drawing the electric field due to sheet 1. Are you clear or not? And when you want to and when you are going to draw field lines due to sheet 2, then there is no need to concentrate on the sheet 1. Okay, you should only and only focus on sheet 2. Are you clear or not?
Yes, sir.
Yeah. So now we can calculate the field here for region 1. In region 1, okay, in region 1, what will be the field? E of region 1 is equal to both of the fields in region 1 is opposite in direction. We can write here E plus of E minus. E plus is in the direction of minus x-axis, or you can say minus I cap. The value of E is sigma over 2 epsilon naught, which we have already calculated. You can write here sigma over 2 epsilon naught minus of I cap plus due to negative charge plate, electric field is sigma over 2 epsilon naught, and it is directed towards plus I cap. So you should write I cap. When you take I cap over 2 epsilon naught as a common, you have, this is your sigma 1 and this one is your sigma 2. You should write here minus of sigma, minus of sigma 1 plus of sigma 2, or you can write I cap
Sigma 2 minus sigma 1.
exactly. sigma 2 minus sigma 1. This is your electric field in region 1. Are you clear or not?
Yes.
Similarly, we are going to calculate in region 2. In region 2, your electric field in region 2 is again E plus of E minus. E plus is sigma 1 over 2 epsilon naught. Sigma 1 over 2 epsilon naught plus I cap plus of sigma 2 over 2 epsilon naught plus I cap. Why? Because both are in the same direction, which is plus I. Are you clear? After calculation, you get field in region 2 is I cap over 2 epsilon naught can be taken as common, and you get sigma 1 plus of sigma 2. This is your value of electric field in region 2.
Sir,
Note it down, please. Sorry.
Sir, why in region 1 it's going both the sides?
Sorry. Hello. I think you are Hamza. Tell me, please.
Sir, when my mic is voice is very low, so I'll message.
Hamza, actually your voice is not clear. Mention your concern okay in chat, please. Hamza, mention your concern in chat box, please. Okay, why is it going both sides in region 1? Okay. All right. Why it is going in both sides in region 1? It is because due to positively charged plate, electric field lines is away from the charge. You can look at here. And due to negative charge plate, it always be towards the charge. Okay, towards the charge plate. Are you clear or not? Causing which in region 1, electric field is in two different directions. Are you clear, Hamza?
Yes, sir. Understood.
Okay. Note it down, please. All of you.
So, sir, for region 3, it will be I cap by 2 epsilon 0, uh, sigma 1 minus sigma 2, right?
Exactly. Good. All of you have noted it?
Yes.
Hello, Akshay,
Yes,
Rufia.
sir. Noted.
Okay, good. In region 3, if you want to see, then you can write here region 3. I hope all of you can easily calculate it now. It is very, very easy. E plus of E minus. You get sigma over 2 epsilon naught. E plus is along plus I cap. It is your plus I cap plus sigma 2 over 2 epsilon naught. It is minus of I cap. You can take I cap over 2 epsilon naught as a common, and you get sigma 1 minus sigma 2. This is your final calculation of region 3. Okay, note it down, please. Aisha, are you clear or not? Good. And another one is Rufia. Rufia, are you clear? Is this question is clear or not, Rufia? Hello. All right. Can we move on?
Yes, sir.
Okay. And now again we are going to solve some derivations, okay, based on the spherical bodies, okay. But there are two different derivations in which, okay, there are two different derivations and both are based on the sphere. In first case, we will consider that hollow sphere, conducting and non-conducting, you can say. I mean, your body is hollow, okay? Your body is hollow. Are you clear? It doesn't matter, it is conducting, sorry, for both conducting and non-conducting. And in the second derivation, we will take it is a solid body, not hollow. Are you clear? So it is two different case. First of all, note it down, please. You are going to understand about here sphere, and this sphere will be of two types. In the first sphere, we are taking, this is your first one and this one is your second one sphere. Okay, this is your hollow sphere. You can take it conducting and non-conducting. Or sometimes it is also called solid conducting sphere. And for this, it is your solid non-conducting solid non-conducting sphere. Note it down, please. Note it down, please. Have you noted it? All of you have noted it or not?
So can you show that again?
Sorry?
So can you go to the previous slide?
All right. Note it down fast, please.
Done, sir.
Next heading, electric field. We are going to discuss this first case. For this case now. Electric field due to hollow, conducting or non-conducting sometime it is also called solid conducting sphere. Please note it down. It can be asked by the name of conducting hollow sphere or by the name of non-conducting hollow sphere, or in another way, electric field due to solid conducting sphere. Are you clear? For all of these three naming, your solution will be same. Are you clear? Are you clear or not?
Yes.
Okay. We are going to consider a sphere of radius r first. We are going to consider a sphere of radius r and having charge capital Q. Okay. Note it down, please. Consider a sphere of radius r and having a charge of capital Q. This is your radius r. Okay. In this case, we will try to calculate the electric field at three different positions. Are you clear? The first position we are taking here outside of the sphere at any point P. Okay. So mention it, please. In the first case, outside of the sphere. When you are considered outside of the sphere, then once again, we are going to draw this sphere here. This is your sphere of radius r, having charge plus Q. Okay, throughout this sphere. Now, we are taking any other point at separation small r, which is your point P. Now, this is your point P. If you want to calculate electric field at this point P, then first of all, we should draw a Gaussian surface. When you draw a Gaussian surface, then remember that your Gaussian surface must be passed from the point which you have taken outside of this sphere. Okay. And we can consider here, this Gaussian surface is of radius r. Now, if we choose an elementary area like ds, then can anyone tell me what will be the direction of unit vector? It will always be perpendicular to the surface, which is your s vector, or you can say unit vector also. Okay. And what is your direction of electric field? As you can look at here, your body is positively charged. So we can say the electric field lines always pass away from the away from the body. This is your direction of electric field. All of you are understanding your pictorial representation? Akshay and Hamza, Rufia and Aisha. All of you are understanding this?
Yes, sir. Yes, sir.
Okay, Aisha, Rufia. Any issue? Now we can write here. Consider a Gaussian surface of radius r. And first of all, we are going to calculate the flux. Then we will calculate the field. Then flux through sphere. This is your phi is equal to integration of E dot ds cos theta, which is phi is equal to E can be taken as outside integration of ds cos theta you can take as 0. Finally, we get phi is equal to E into S. Integration of ds will be S. Cos theta is 0, which is 1. Finally, you can write E into your area of this sphere is 4 pi r square. Okay. This is the flux. This is the amount of flux passing through this Gaussian surface of radius small r. Okay. We can consider it equation number 1. Now, using Gauss law, we have phi is equal to Q enclosed over epsilon naught. What is your value of phi here? We have value of phi is E into 4 pi r square. What is the Q enclosed? The total charge enclosed within the within the Gaussian surface is considered as Q over epsilon naught. As you can look at here, the surface charge density is sigma here. Just 1 second. After solving it, Q over 4 pi epsilon naught r square. This is the value of electric field in terms of charge. Okay. When you want to calculate the value of electric field in terms of density, okay, then you can write here in terms of density. You can write your value of Q is 1 second. Sigma is Q over S, or Q is equal to sigma into S. Okay. What is your S here? S is your area. Once again, you can write here, what is this S? S is your area. Okay. Total surface area of this sphere. If you are taking total surface area for this sphere, then your radius will be capital R, not small r. Okay. This is your 4 pi capital R square. Okay. Note it down, please. Then we will continue it in the next page. Please note it down till here. All of you are understanding till this point. I mean, or not?
Yes, sir.
Akshay and Hamza, Rufia, Aisha, all of you are clear till the end point here.
Yes, sir.
Rufia, can you hear me? Note it down, please. Have you noted it, all of you?
Yes, sir.
Yes, sir.
Okay. Look at here in this part. We have Q is equal to sigma 4 pi r square. Okay. Where r is your capital R square, which is the radius of sphere. All right. Now put this is your equation 1, this is your equation 2. You can consider and consider it equation 3. Put 3. Put your value of 3 in 2. When you put value of 3 in 2 at the position of Q, you get E is equal to sigma 4 pi r square over 4 pi epsilon naught small r square. 4 pi is cancelled with 4 pi. Finally, you get E is equal to sigma capital R square over epsilon naught small r square. Note it down, please. This is your final equation. Okay. Have you noted it? Now, this is your outside of the sphere. In the second part, we will calculate at the surface. At the surface of the sphere. Okay. We are again going to draw the sphere. This is your sphere. Of radius r. And we are going to calculate the field at the surface of the sphere. Remember that it is very difficult to draw the Gaussian surface at the same line, I mean on the same sphere, but just for clearance, I am going to draw by touching it. You can imagine that this Gaussian surface is passing through this point, touching the surface of the sphere. Okay, just like this. You can consider it. Okay, and we are considering here again your radius of the Gaussian surface is equal to the radius of the sphere. Okay, radius of Gaussian surface is equal to the radius of sphere. Now, what is the flux through sphere? Flux through sphere, it is your phi is equal to integration of E dot ds cos theta. Again, you can consider cos theta is 0 because your body is positively charged. We have already know. You can take it positively charged, and the area vector and the field vector both are in the same direction. You can draw here also. This is your field vector and this is your area vector. Okay. So phi will be E into integration of ds cos 0, and phi is equal to E into S, which is phi is equal to E into 4 pi r square. We can consider a capital R now. Why? Because your radius of the Gaussian surface and the radius of the sphere is same. This is your equation number 1. And then for calculation of electric field, we should use Gauss law. Using Gauss law. Using Gauss law, your phi is equal to Q enclosed over epsilon naught. Phi is equal to Q enclosed over epsilon naught. This is your equation number 2. Put 1 in 2. When you put value of 1 in 2, you get E into 4 pi r square is equal to Q enclosed over epsilon naught, which is E is equal to Q enclosed can be considered as Q 4 pi epsilon naught r square. This is the value of electric field. Okay. If you want to calculate it in terms of density, then you can again mention here in terms of density. We know this is your surface charge density again. Sigma is equal to Q over S, or Q is equal to sigma into S, which is equal to the sigma 4 pi r square. I mean capital R square. This is our equation number 4. Put equation 4 in equation 3. You get E is equal to sigma 4 pi capital R square over 4 pi epsilon naught capital R square. 4 pi R square cancel 4 pi R square. You get E is equal to sigma over epsilon naught. This is your E at surface. Okay. Note it down, please. Note it down, please. E at surface is sigma over epsilon naught. Okay. All of you are understanding, Akshay and
Yes, sir.
yeah, Akshay, Hamza. Any issue? Aisha, Rufia.
No, sir.
Okay. Good. Note it down, please. Have you noted it?
Yes, sir.
Hello. Okay. This is the value at the surface. Okay. And now, in the next part, in case 3, inside the sphere. We are going to calculate now inside the sphere. Again, consider the sphere. This is your sphere having positive charge. Radius of this sphere is capital R. Now, we are going to calculate the electric field inside this sphere. Suppose that we have chosen a point P here and we want to calculate at this point P. What will be the electric field? First of all, you should draw a Gaussian surface which is passing through the you should draw a Gaussian surface which passes through this point. All right. The radius of this Gaussian surface is small r, and we know if this body is a conducting body, then inside the conductor, the net electric field is 0. So we can write here using Gauss law. Using Gauss law, your flux is Q enclosed over epsilon naught, where Q enclosed is 0. So we can write here phi is equal to 0. You have already know, I think, due to the electric charges always resides at the surface of the conductor. Okay, it never resides inside the body of the conductor. Are you clear or not? So we can write here E inside is equal to 0, or sometimes it can be also said to be the E center is 0. Okay, this is your calculation of inside the sphere. Note it down. Then we will discuss the graph drawn from for all of these 3 conditions for this heading. Note it down, please.
Done, sir.
Okay, good. Good. Now, all of you, please concentrate on the screen for better understanding the graph. We have now 3 equations. Electric field at outside, we have calculated. What is the electric field at outside? It is sigma r square over epsilon naught small r square. The second one, E at the surface. E at the surface, we have calculated sigma over epsilon naught. And the third value of electric field, which is E inside, is
0.
0. Are you clear? What are you understanding here? Just 1 second. 1 second, please. I am going to write here E surface is sigma over epsilon naught. And the third one is E inside is 0. Now, look on all of these three equations, please. First of all, we are going on E inside, which is 0. I mean, it doesn't matter, okay, what is the value of the electric field, because it is 0, okay. There is nothing to discuss here for E inside. Are you clear or not? Now, for E surface. E surface, in this equation, you can look here, there it is independent on R. R in the sense you can say radius or separation, you can say, okay. It is depends on R or not. Look on the equation. E surface is equal to sigma over epsilon naught. This means we can say it doesn't depends on the R. Hence, we can say if it doesn't depends on the R, we can write here independent on R. Are you clear or not? Hello?
Yes, sir.
All of you understanding? Akshay, Hamza, Aisha, Rukia, all of
Yes,
you
sir.
understanding? Okay. Now, the next point is E outside. E outside makes a relation between R is 1 over R square. Are you looking or not for this? E outside is 1 over R square. Are you clear or not? We can write it. Hello? We can write it or not?
Yes, sir.
Okay. Then what will be the graph drawn for E outside? I think it is hyperbola. This is your R and this is your E, and your graph should be drawn like this. Are you clear? But in this part, we are going to draw all of these three values of E simultaneously. Okay? No need to draw this or this individually. Okay? First of all, we are going to draw a sphere here. This is your sphere. This one is the sphere. And we are taking at the center. This is your x-axis. Sorry, this is your y-axis and this one is the x-axis. Are you understand it? We are taking here, the radius is r. This is your radius r. This is the position of O. And for E inside, there is no any graph. Okay, there is nothing to discuss here for E inside. We are coming on E surface. For E surface, you can look at here. This is just 1 second, please. This is your R axis and this is your electric field axis. And now, can anyone tell me what will be the graph drawn for E surface? You can look, it is independent on R. Then we can easily say that the graph of independent of R will be along this. I mean, a perpendicular line on the R passing at R surface. Are you clear or not? This represents independent on R. All of you are understanding or not?
Yes, sir.
Okay. But this is the graph of sigma over, one second, sigma over epsilon naught. This is the position where R is equal to 0. I mean for E inside, you can say. And this is the position where your R is equal to capital R. Okay. One second. Origin here. And this is the position for where R is equal to 0. And this is the position for R is equal to capital R. And in between R is equal to 0 and R is equal to capital R, this position will be R is always less than R. Are you clear? Are you clear or not?
Yes, sir.
But when we go beyond capital R, I mean when R is greater than R, then you can look E is outside and your graph will be like this hyperbolic. And this hyperbolic graph can be drawn from this position in such like this. Are you clear or not? Hello?
Yes,
All
sir.
of you are clear or not?
Yes, sir.
All of you understanding?
Yes, sir.
Akshay, Aisha, Hamza, Rufia, all of you understanding this graph or not? This curve represents E is inversely proportional to R square. I mean E outside. You can also mention here E out, which is inversely proportional to R square. And this region is R is, small r is greater than capital R. Are you clear or not?
Yes, sir.
And for R is equal to R, this represents surface. R is equal to 0 represents center. Okay. Are you clear here?
Yes, sir.
And this one represents outside. Okay. Note it down, please. Sorry, draw this graph, please. Hence, we can say from R is equal to 0, from R is equal to 0 to the R is equal to capital R, there is no field. Why? Because your body is conducting. Are you clear? Are you clear or not?
Yes, sir.
Please note it down first. Then I will write some point to understand it. Okay, further for you. Note it down, please, first. All of you have noted it?
Yes, sir.
Hello, all of you have noted it? Aisha, Rufia, Hamza. Hello.
Yes, sir. Done.
Note it down, please. E inside. E inside is 0. Why? For conducting. I mean body is conducting here. Are you clear? Or you can say from R is equal to 0 to the R is less than R. Electric field E at surface is maximum. Okay. Why? It is R is equal to the R. And E outside is E outside decreasing. Just 1 second. E at surface is constant. It is a constant value at R is equal to R. E outside is decreasing when R is greater than. Are you clear? These are the 3 important points which is important to remember to all of you. Okay? Which explains whole of this graph at once. Are you clear?
Yes, sir.
Yes, sir.
Aisha, Hamza, Rufia, and Akshay. Any
Yes,
issue?
sir. No.
Okay, good. So today our time is over and we will meet in our next class. For today, bye-bye. Right? In the next class, this unit will over. And we will also start the next unit, electric potential and capacitors. Okay?
Yes, sir.
Okay, sir.
Thank you to all of you. Bye.
Thank you, sir. Bye, sir.